And hello YouTube, welcome back to our turbulence modeling video series. Today we're going to talk about, we're going to continue on our natural convection smaller scales discussion. So in the last video, we talked that, we said that the RA tau, the friction Reynolds number was pretty high. And it's about a few thousand where we are normally used to 180. But this because of the way the scaling works. Alright, this is because of the way the scaling works. You know, the Reynolds number for a flat plate and for a pipe, they are vastly different. But it's when you look at the amount of friction that it has, it's more or less the same. So let's take a look at our estimate for length scale. So we use the same formula. X equals to the smallest dimensionless distance separation, which we use 0.05. We use L over the Reynolds number, and we get 0.006 mm. And this is the absolute smallest length scale you'll ever need to resolve. No smaller than this, because this is really, you know, overestimating it by a lot. Overestimating the friction forces at play by a lot. And if we take a look at a different length scale, based on the using the buoyancy velocity, which is you know, based on the Graw number, that means to say I just chuck in the Graw number into the CFX. We'll get and we repeat the same process. We will get 0.02 mm, and we can see that this is on the same order of magnitude as 10 times smaller, is about 10 times smaller than the Kolmogorov for bachelor scales. This is pretty good estimate. You can see the Kolmogorov scale is about 0.5 mm, bachelor scale about 0.6, here's 0.02, so just divide by 10. So you more or less get the ballpark figure there. Alright, so let's now compare with the hardcore estimates, the more hardcore way, where you want to take a look at this all of these wall functions, which are based on the temperature length scales and the velocity length scales near the wall, based on wall functions for natural convection. So if you recall, where did we get our wall functions from? These are from, they're from here. We talked about that in the last video. You can see Yen, Moser, and Suter, all of this stuff. So I'm going to quickly go through them. Here we are. We actually scale with this heat flux velocity and of course alpha, and that is our temperature length scale. For dimensionless velocity length scale, it is based on heat flux velocity, friction velocity, and of course alpha. So it's actually this y1 star star, which is the velocity length scale, is actually the temperature length scale, and then you multiply it by this uq over u tau squared, which is the heat flux velocity over friction velocity squared. And what is the heat flux velocity? It is all of this stuff, G, beta, alpha, etc, etc. These are for natural convection. Of course, you have the Q of the wall. Alright, so want to make it easier, because if you take a look at this, you know, trying to calculate all of this will be quite a headache. So let's try and make it look more like it's made out of dimensionless numbers. So I mean, the interesting thing we want to calculate is this uq over alpha. So let's try calculating uq over alpha. So I'll just say alpha over, alpha over, I mean 1 over alpha times uq. uq is this thing here, so it's just copy and paste over here. So let's try chugging in the Rayleigh number first. So Rayleigh number is here, which is G beta times the temperature difference. Then you have a length scale, which is the height of the square. Then u and alpha is there. So I make G beta the subject, then I will have this expression here. And I can substitute G beta into here by copy and pasting all of this into here. And the result is I'll get this messy thing here. So let's tidy it up. Bring the TH minus TC, the temperature difference, into the denominator, H cubed into the denominator. And I'll combine this alpha over here with this alpha over here. So I'll just get this expression over here. Alright, so next thing, we want to get rid of this Q wall and TH minus TC. So how do we get rid of that? We try and replace it with the Nusselt number. What is the Nusselt number? The local Nusselt number is, of course, the local heat transfer coefficient times some length scale over the conduction, the coefficient, the conductivity. Okay, and what is H? H is actually the Q at the wall over the temperature difference, characteristic temperature difference. So the local Nusselt number is defined as such. You have Q over the temperature difference between the hot and cold wall. Then you have the length scale, and then you have K. So this length scale I'm using here is H, L equals to H. The length scale I'm using is this cavity height, which is the side of the square. And then we make this Q over TH minus TC the subject, so that I can get rid of this Q wall and this TH minus TC. Then I have the local Nusselt number times K over H. That is what we can substitute in. So we have this equation again. I'm just going to copy and paste that into here. So I took the TH minus TC out. And we have the Q wall on top. And we have it here. And we just bring the H to the bottom to make it neat. So we have two dimensionless numbers here already. So that's good. Alright, so let's tidy things up further. You notice that K over rho Cp, that's actually just alpha. So we just combine alpha into K over rho Cp. So we get alpha cubed here instead of alpha squared. Alright, we're almost there. We just want to get rid of this nu so that we don't need to know all these parameters explicitly. So I'm going to replace nu by alpha times the Prandtl number so that we have more dimensionless numbers in there. And then we have alpha to the fourth. Alpha to the fourth, we can actually just bring this out along with h to the fourth. You take the 1/4 power, then you have alpha over h outside. So at the end of the day, we have uq over alpha equals to these three dimensionless numbers over h. So that makes uq relatively much easier to calculate. Alright, so uq equals to alpha over h times these three dimensionless numbers to the power of 1 over 4. So let's try and calculate our temperature length scale. So we just substitute this uq over alpha into here, then we'll get this expression, and then we want to get the y. We want to get the y spacing for a y star of 0.05. That's a good guideline, the smallest dimensionless velocity scale. So just like we use the smallest delta x plus is also 0.05. Then we get this correlation here. We have h over these three dimensionless numbers, and we substitute the Nusselt number as scaling as 1 over cube root of the Rayleigh number, and then we have this very neat expression. So we need the Prandtl number, the Rayleigh number, and the height scale. So the Prandtl number and the Rayleigh number are as follows, or the Rayleigh number and the Prandtl number as follows, and h is as follows. And the thermal length scale is about 0.03 mm. So if you take a look at our not so rigorous methods before, you see it's about the same. The same order of magnitude, 0.02 here, based on just substituting the Graw number here into some flat plate correlation. So actually this is not too bad, and actually this is a conservative estimate. As you can see, this is actually slightly smaller than, let's say, than this thing over here. This is actually smaller. So this is about the smallest length scale we need. Okay, and it's about 10 times below the bachelor scale and the Kolmogorov scale as well. So now let's just check with the momentum boundary layer scales. So we have our y star over here, y star here, and uq over u tau. So uq over u tau squared, uq over u tau squared. We want to make our life easier by treating them in terms of dimensionless numbers. So how can we make uq into some dimensionless number? So remember the friction Reynolds number, and that is u tau times some length scale over this kinematic viscosity. Now we try and make u tau the subject, so that we have Reynolds number times nu over L, and that becomes u tau. And for uq, we see that UQ has already been fashioned or compressed into a lot of dimensionless numbers, which makes it a lot easier for us. Okay, so we have the dimensionless numbers as such. We have alpha, and then here is a square, and then we have nu squared, and then you see the h and the l. Since they are both talking about the same length scale, I'll just cancel them out because h equals to l. I mean, the length scale I'm talking about in the friction Reynolds number is of course the height of the square cavity. And by doing so, I cancel out the length scales and it makes life a lot easier. So right now I have these three dimensionless numbers on top, Reynolds number, the friction Reynolds number at the bottom, and you have alpha and nu, which conveniently that is our Prandtl number. So I bring Prandtl number into the denominator, and then we see that this relationship between the friction velocity and the heat flux velocity is just this collection of relatively simple dimensionless numbers. Now, of course, we want to get velocity scale, or rather the velocity length scale, so we still need to substitute all of this in, and that's very easy after doing all this work. So we have uq over u tau squared being this, and of course y uq over alpha. We already have uq over alpha, which you just substitute this over here, so that makes it pretty straightforward. Okay, so then we can just collect all these dimensionless numbers together to form this. We form this, and right now we just take the Nusselt number and we plug in this little relationship. This Nusselt number scales as Rayleigh number to the 1/3 cube root, and then we just put this in here, and we get a delta y star. Okay, so doing so, skip a few steps. I'm simplifying things a bit, substituting and simplifying, and we take a y star equals 0.05. So what I'm doing is I just make y the subject, and that will result in this equation. Substitute this, and RE tau being 2380. Okay, and we find that our velocity scales are 0.08 mm. That's an estimate. So this is an order of magnitude estimate for the velocity scale. Excuse me. Yeah. So anyway, this is our velocity scale estimate. Looks like our rule of thumb really works as a lower bound. If you take a look at a lower bound, if you take a look at the lower bound, which is over here, 0.02 mm, which means we take the buoyancy velocity as if it was a flat plate problem, and our buoyancy velocity will become the free stream velocity. Then we use the friction correlation over there, and you will get us this number over here. So that's perfectly fine. In terms of this becomes our lower bound. We don't see any length scales actually going below this number. Okay, even our temperature length scales is about there, and our velocity length scales aren't very much bigger as well. Okay, so now we want to check all this with experimental data, where I will use this vigorous length scales. Now not with all of these correlations, but rather try to get some experimental data here. So again, we'll need and this is actually done by Ampofo, and I don't know how to pronounce his name, but so these guys actually did a square cavity natural convection case, and actually they had a lot of they calculated the Nusselt number. All right, they actually got the Nusselt number out, and from this case UQ is calculated as follows, and I picked up the maximum Nusselt number. Okay, the maximum Nusselt number is about 138. All right, and a special interesting note that our heat transfer coefficient or the Nusselt number, it's calculated as 0.15 times Rayleigh number to the cube root. Okay, So actually there's a 0.15 coefficient in front, which I kind of just neglected to add in. So we can see what this difference actually makes. I mean, by substituting, of course, this Nusselt number in. But we see that the scaling is more or less correct. That it scales with the cube root of the Rayleigh number. Of course, you need to consider this coefficient in front, because that's about an order of magnitude lower. But anyway, that's an error I made by simplifying things. But let's see how much this error actually impacts our length scale. Alright, so the wall shear stress is as follows. So this actually helps us to determine UQ. We can substitute it in later. But we also need our wall shear stress. Wall shear stress is about this much, 1.72 times 10 to the minus 3 Newton per meter square, or pascals. And we get air density estimate, okay, for small, if you want a conservative estimate, we take the smallest air density, and that is about 1.23 kg per meter cube. I took it from this engineering toolbox, roughly at 50 degrees C. You roughly try and read off the graph, and we find the friction velocity is about 0.03, 0.04 meters per second. And when we calculate our friction, so-called friction velocity, or rather the friction Reynolds number, because now this time it's really based on the wall shear stress that is experimentally determined. We see that, hey, our wall shear stress, our friction Reynolds number, is actually about 1402, and 1402 is actually lower than, let's say, you compare it to here. If we use that flat plate method, by just substituting the square root of the Grashof number into the flat plate friction factor correlation, we get about the same order of magnitude, which is pretty good. And actually, this is a conservative estimate as compared to the real friction Reynolds number. Okay, so this is pretty good. That kind of validates the way we do things. Okay, especially for square cavity. So this method of getting a friction Reynolds number in terms of just the square root of Grashof number, it seems to work. Okay, so it's not too bad. This is actually pretty good. Okay, so next thing, we want to try and validate our temperature scales. So let's try substituting all the relevant numbers in. So the Prandtl number is about 0.71. Rayleigh number, of course, 1.58 times 10 to the 9. Nusselt number 138. So I just plug and play all these numbers, and I plug in the characteristic height, and all of this together is about 836. Calculate in Excel. So we have y 0.05 over 836. Actually, that gives you about 0.06 mm for this smallest mesh size. And we see that the temperature scales here are a little bit bigger than, let's say, this thermal temperature scale we used using our really rough estimates. So it's on the same order of magnitude. In fact, our estimates are a bit conservative in that sense. So that's a good news. How about velocity scales? If we substitute all the dimensionless numbers back in, this time using the friction Reynolds number of 1400 and the Nusselt number of 138, and we do so, by doing so, you just plug and play all these numbers in, we get about 249 here, and we just get a y as a function of this factor times delta y star. So delta y star is we want that velocity scale spacing to be about 0.05, and we find that after we do all the math, the velocity spacing is actually 0.15. So this is on the same order of magnitude as the Kolmogorov and Batchelor scale. So it seems that, okay, this 0.06 mm is actually a very good, is actually the velocity scale or the length scale you need. So if you notice this 0.06 mm, that is basically just 1 over 10, 1 order of magnitude lower than this eta k, which is, this is the Kolmogorov scale. So for fairly low Reynolds numbers or Grashof numbers, where you just enter like low level of turbulence, you just take this Kolmogorov scale and you divide by 10, and that will be your smallest mesh size. It's a very easy rule of thumb there. And of course, our bachelor scales, you just scale it with the Prandtl number. If your bachelor scales are smaller, then you use the bachelor scale, divide by 10, and there you will have your smallest length scale that you need. Okay, so that isn't too bad here. Okay, so it makes this whole thing a lot easier, and this exercise kind of shows you that I mean, taking the Kolmogorov scale or the bachelor scale, you just divide by 10. Using that for the smallest mesh size is actually pretty reasonable estimate. Okay, so it's not too far off. It's pretty good, and that actually should give you a proper DNS simulation if you need a DNS, direct numerical simulation. Or else, of course, you scale it properly. You want your Kolmogorov scale, you times 10, you get LES grid. You times 100, you should get the finest Rayleigh number grid. So that's all we are doing here. So it should be pretty straightforward after this. Okay, so now conclusion. Okay, smallest mesh size is about 10 times smaller than the Kolmogorov or bachelor scale for natural convection and forced convection. Convection at low turbulence. Okay, low level. Okay, what is low level? That means just after transition, not 100 times bigger, because we only do about 1 to 10 times of that, and we see this relationship actually being pretty good. Okay, so we see that this is actually a very reasonable mesh size estimate. It should give you the good pop-up figure for your mesh sizing, and it's a very quick way. You just calculate Kolmogorov or your bachelor scale, just divide by 10, and that is your smallest mesh size. So that should help you get started with meshing for turbulence modeling. Okay, yeah, and of course for mixed convection, you want to check your Richardson number, and you want to see if the natural convection Kolmogorov scale or the forced convection Kolmogorov scale is smaller. Okay, if it's a low Richardson number, of course we tend to use the forced convection scale. If it's a high Richardson number, meaning 10 and above, natural convection will dominate, then we use the natural convection Kolmogorov scale. So that's just something to be mindful about. So thanks for watching. Thanks for watching this video. Hope that's helpful in telling you how to size your mesh properly, based on all these wall functions and dimensionless estimates. So do leave a like and subscribe if you find it helpful, and see you guys next time. Bye bye.